In this video, we're going to talk about how do you add matrices together and how do you scale them, and by that I mean how do you multiply them by some constant. Okay, so the first observation I want to begin with is we've seen before that the set of m by n matrices, that's the same thing as the set of linear transformations from Rn to Rm. Like anytime I have a matrix, I can rewrite it as a linear transformation from Rn to Rm, and vice versa. If I have a linear transformation like this, I can write it in matrix form. So what I want to do is, I want to begin by thinking, let me try the next one. Thinking of things we can do with functions. And the reason why I want to do that is because linear transformations are a special type of function. Linear transformations are just special functions. So let's think of the things that we can do with functions and see if we can do those things with matrices, because we should be able to. Linear transformations can always be written as matrices. Okay, so we can add and subtract functions. We can also scale functions. We can multiply functions by a constant. We can also compose functions. By that I mean form a composition of functions, like f of g of x, a composition of functions. So those are some things that we can do with functions. So let's translate these to matrices. So what I want to do is, I want to keep track of two columns. One where I look at what these properties will look like in terms of matrices, and another column where I look at what do these look like in terms of functions, in terms of linear transformations. So I'm going to begin by saying that A and B are just two matrices that have m rows and n columns. Okay, so I've written them in terms of their columns here. Oops, I forgot to put a subscript there, A1. So in the context of linear transformations, the transformation for A associated to A would be T sub A, and that goes from Rn to Rm. And then similarly, the transformation associated to B, let's call it T sub B, goes from Rn to Rm. So what I want to do now is I want to define how we add two matrices. So the way we define that addition is, you just add the first two columns together, so A1 plus B1. So you add those first two columns together. This is going to be the first column in A plus B. And then you do that all the way through for every single column. So up until the nth column of A, added to the nth column of B. So this is going to be column n of the sum. So writing this another way, what we do when we add two matrices is we do a term by term sum. Okay, so we'll see what that looks like in an example in just a couple of minutes. Okay, so in the context of functions, if I wanted to write down the transformation for the sum of these two matrices, so the transformation for A plus B, that's equal to the transformation that's associated to A plus the transformation that's associated to B. And what this side means is it's thinking of this as a sum of two functions. T of A and T of B are functions, so when we add them, we're thinking of this as a sum of functions. So in other words, i.e., if I were to take these two functions, add them together, and then plug a vector x into that, what does that equal? Well, that equals what we get if you plug x into T of A plus what you get if you plug x into T of B. Okay. So next, let's define what it means to multiply a matrix by some constant c. So what you do there is you multiply c by each of the columns of A. So you'll do c times the first column, up until c times the last column. So saying this another way, what this does is each entry in the matrix is multiplied by that constancy, whatever that number is. So in terms of linear transformations, if we write down the transformation that's associated to the matrix C times A, so C times A, let me make the C appear smaller, lowercase c, and then capital A. So what this is, it's the same thing as the transformation associated to A, but with a C in front. Okay, so this is T of A, the transformation associated to A, multiplied by the constant C. So on the right-hand side, we're just writing down some properties of functions. On the left-hand side, we're looking at, well, what does this look like in terms of matrices? So we've written down a formula to add two matrices, and a formula to multiply a matrix by a constant. Okay, so I know this seems kind of abstract right now, but let's do an example, and it's actually pretty easy. Okay, so let's compute the following. So I don't want to peek too far ahead. So in part A, I have these two matrices, and I want to add them together. To add two matrices together, we just do a term-by-term sum. So I will take the first, entry in the first row, first column here, first row, first column there, and add those together, and if I do that, I get 2. Then I do the second entry in this row, second entry in that row. If I add them together, I'll get 5. And if I keep going like that, well then 5 plus 5 is 10. 2 plus negative 1, that's 1. 4 minus 3, well that's 1. And then 6 minus 6 added to negative 8, that is negative 2. And that's how I add two matrices together. I just add them term by term. So yeah, not bad. Okay, and then multiplying a matrix by a constant in front means that each entry in the matrix gets multiplied by that constant. So if I do 3 times this 2, I'll get 6. 3 times this 3 is 9. And then on the bottom row, I'll get 15 and 21. So that's how I multiply a matrix by a constant. Okay, so I'm going to end by stating a remark, which is when we add two matrices, or when we scale a matrix by a number, this requires that the matrices have the same size. That's important if I add two matrices, because then I need them to have the same size. When I multiply a matrix by a number, the size of that matrix is not important.